So there are some definitions. Let's revise that. Let X be a metric space with metric D, then the distance between the points X and Y is written as dxy instead of mod of x minus y. So dxy refers to the distance between x and y in the metric space X. Second definition, let X and Y be metric spaces and let E is subset of X. So we are having a mapping F from this E to Y, where E is a subset of X. So we are taking the mapping from E to Y, be a function, and let P be the limit point of E. Then limit x tends to P, f of x is equal to Q. Now here x is tending to P, where x is belonging to this E only. Now since x and P both are belonging to the X metric space, and this P is a limit point of this E, so P may or may not belongs to E. So x is tending to the limit point P. F of x is equal to Q, where Q is the point in Y. So we mean for every given positive epsilon, there exists delta positive depending upon epsilon and Q belongs to Y, such that, now this is the definition for this limit x tends to P fx equal to Q. What we will be having, such that dy fx comma Q less than epsilon for all x belonging to E, for which dx for x comma P is less than delta and also greater than 0. What this dy means? This means distance in y between these 2 points fx and Q, and dx means distances in x, taking the points of x. So dx is the distance in x and dy is the distance in y, and P may or may not belongs to E. See, this is your metric space X and this is Y. We have taken E to be the subset of X, and let P be the limit point of E. Then P may belongs to E, may not belongs to E, since it is a limit point, right? So what we are having a mapping from this E to Y. And for that mapping, what we have this, let x tends to P fx equal to Q, which means for epsilon positive there exists delta positive depending upon this epsilon, and Q belongs to Y such that distances in Y is less than epsilon for all x belonging to E, for which distances in x is less than delta. So whenever you take the distance in Y, we should take that distance less than epsilon, and for which the distance in x, whenever we are taking the distance in x, that distance we should take less than delta, right? So this is a very important definition which is used in the coming theorem, in the proof of the coming theorem. Third is, if x and y are replaced by real line or complex plane or Euclidean space Rk, then the distances dx and dy, these are replaced by absolute values, right? Okay, let's start with the theorem. This is a very nice theorem. Let x and y be metric spaces and E is a subset of x. We are having a mapping from E to y, and let P be the limit point of E. Then limit x tends to P fx equal to Q if and only if limit n tends to infinity f of Pn equal to Q. Now we have to prove the both ways. For every sequences Pn in E such that Pn is not equal to P, these two are distance. Now Pn is not equal to P means there must be some distance in between these 2 points Pn and P. Between the points of the sequences with P, there must be some distance. And limit n tends to infinity Pn is going to be equal to P, right? Let's start with the proof. Fine. Now we have to prove the both ways. we will start from here. So I suppose limit x tends to p, f of x is equal to q. Now I'm writing the definition for this, what we have revised in the remarks. So taking let epsilon to be positive, this be given, then there exists delta positive depending on epsilon such that what we are having, distance in y, taking the distance in y, f of x, and the other point in y is q. This distance is less than epsilon for all x belonging to E, for which distance in x is less than delta, for which distance in x, points of x are x comma p, this is less than delta. Just take this as your 1. Now what is given to us? Since limit n tends to infinity, Pn is equal to P. Now this is also given. So for this, let's write the definition for the convergence. What does this mean? There exists a positive integer n depending upon delta. Why delta? Because we are taking the distances in x. That's why. Such that distance in x. Now Pn is a sequence in x, right? So Pn with P, this distance is less than delta for n greater than equal to n, right? Okay. Why I'm taking this distance? Because Pn is not equal to P, it is given to us, right? Therefore, there must be some distance between Pn and P. Okay, thus n greater than equal to n implies this distance 0 less than dx Pn comma P less than delta. Fine, which implies, now for this, what will be the distance in y? If here, see, if we are having distance in x, the first one to be as x, first point is x and the second point is P. For this thing we are having in distance in y, f of x comma q. So if there is x, we take f of x. See, right? And if there is P, we are taking the same thing as q. So here now x is Pn. So replacing this x with Pn. So when I write distance in y, I should write f of this x, which is Pn, f of Pn, right? Comma. If there is Pp, I must write q. Fine. For this distance in x, the distance in y will be f of the first point, comma q, right? Where q is a point in y and p is a point in x. So this distance is less than epsilon. Now since distance in y, f of Pn, comma q, this is less than epsilon for n greater than equal to n. I got this distance from this definition. So what does this mean? Epsilon was arbitrary. Therefore, what does this actually means? Limit n tends to infinity, right? F of Pn is tending to Q, or this is equal to Q. Or you can say f of Pn tending to Q as n tends to infinity, right? So on the other hand, we can also write it as limit n tends to infinity f of Pn equal to Q. So one way it is proved. This we need to prove, okay? Now the other way. Suppose converse. Suppose limit n tends to infinity f of Pn equal to Q is given. See. Now suppose this is given. We have to prove this thing. We prove this result by contradiction. Now this is given to us and I have to prove this, and I will let this to be not equal to Q. Okay? I will prove this result by contradiction. Now what is given to us? Converse suppose limit n tends to infinity f of Pn is equal to Q. This is given. And if possible, suppose what we have to prove is limit x tends to P f of x equal to Q. This I have to prove, but I suppose if possible this is not equal to Q. Okay? Now according to the definition for limit x tends to P f of x is equal to Q, now the definition for limit x tends to P f of x not equal to Q will become the reverse. That is, then there exists some epsilon positive such that for every delta positive there exists a point x belonging to E which depends upon delta for which distance in y, that is f of x comma q, this distance will now not less than epsilon but greater than equal to epsilon, because I have supposed this not to be equal to q. If f of x is equal to q, then I will take this distance to be less than epsilon according to the definition. But now I am supposing this not to be equal to q, so the definition is reversed now. But distance in x is less than delta. X comma p, right? Because this distance is for which distance in x is less than delta, right? So this would not change. Now I choose this delta to be equal to 1 by n. Why I am choosing? Because I have to see the limit n tends to infinity. So I can choose my delta to be 1 by n. I can choose any one of delta. Delta should be positive. So let's choose, if I choose delta to be 1 by n, where n is your natural number, and I'm taking this Pn such that, now replacing x with Pn and delta with 1 by n, because Pn is a point of metric space x now, that's why. So this is nothing, so what is the distance in x? That means distance between the points in x. So I'm taking Pn with P and letting my delta to be 1 by n. Then clearly what I'm getting, if I take limit n to infinity, then this Pn will tends to P. So clearly Pn will be tending to P, as n tends to infinity. Right? Okay. Now to the above definition. Now here also I will replace x with Pn, right? Now because I replace my x with this Pn, right? According to this distance, what will be the distance in y? Distance in y will be f of Pn, x is replaced with Pn, comma q is greater than equal to epsilon, for which distance in x is Pn p less than delta. Right? Now with this definition, what I'm having, because this is the definition for this, so for this definition I will replace again x with Pn. So according to this, I'm having limit x tends to p, f of Pn is not equal to q, right? As distance in y is this, for distance in x is this. Now x is tending to p, that means x is replaced with Pn for this definition. So if I replace this x with Pn tending to p, can I write instead of Pn tending to p, because Pn will tends to p as n tends to infinity. So because I'm having the terms Pn, I must write instead of Pn tending to p limit n tends to infinity. Now what is given to us? Limit n tends to infinity f of Pn equal to q. But here limit n tends to infinity f of Pn is not equal to q. Contradiction comes. So our supposition was wrong. Therefore, I am inserting one page. Let the color be white. So our supposition was wrong. Contradiction comes. So our supposition was wrong. Hence, limit x tends to p, f of x is equal to q. Hence the result. So both the ways result is proved out.